are we faster than Bun?
Have you ever marveled at the lightning speed of Bun? It's a phenomenon that's left many of us scratching our heads in awe. Today, my friends, I stand before you an audacious objective. I'm on a mission to outspace Bun's package manager. Yes, you heard me right. In this episode, we're aiming to surpass Bun's clean installation speed. In part 2, we'll add caching for lightning fast results.
Okay, so I've implemented a command parser, so what happens is it runs the handle args command, and then it will parse the command and execute it. When we call the parse function here for the installer, it first makes sure it's got the argument, and then it parses the package details. So we split it by the @, which separates the name and the version. And then I ran into a little bit of a dilemma, because parsing versions is an absolute pain, because there's so many possibilities. But then I was saved by the Semver crate, because there are so many different possibilities. There's so much, I just did not want to deal with this. So what we do is we use that to parse the raw version, and then once that's all parsed, we set self.packageName and self.packageVersion, which can then be used in the execute command. This is really good. We've got everything working correctly for the parsing, and now we can get on to actually making the command. Okay, so the next thing we need to do is be able to resolve the versions as fast as possible, because we need to read the version and then know where to look in the registry to get the dependencies for that version. What we first do before doing any HTTP request is we check if we can resolve the full version, which is this function just here. If we can resolve the full version, then it returns a string or the latest version, but otherwise it returns none. If we can resolve the full version, then we make a request to the package and get the specific version. Now you'll notice that this is only 2.83 kilobytes, but if we got the full package data, this is 237 kilobytes. If the full version is not there, or we're not able to get it because of the way that they're parsed, we are going to have to make a request to the full version, which is something we do here. Now notice in this HTTP struct how we're using this header here, which is suggested by the npm documentation. You can see the difference between doing this without a header, which takes 2.7 seconds, and with the header, which takes 1 second. I'm not entirely sure what this does, it's very vague in the documentation, but it definitely decreases the body size that is sent over. Okay, so I've already recorded the explanation for this function, but I did a share explanation, so I'm going to do it again. When parsed, the available versions hash map is actually scrambled up in the wrong order, and it's really irritating that CERD does this. But because this is a rare case, I think it's fine for now just to convert this to an array and sort it. Now, if they're using the less operator, there is a slightly more efficient way to do this than what we do down here. So what we do is we get that version position in the hash map, which is now a vector, and we get the item before that, so that makes sure that we get the latest possible version, which is less than the version provided. Worst case scenario, we are going to have to loop through every single version the package has and find which one matches the semantic version. This matches function is really useful, provided by the Semver crate. Once we do that, we finally call the install package command. Now I'm probably going to change this because we need to use some multi-threading. So if I actually run the release and get all of these packages, with multi-threading, it only takes 500 milliseconds. To compare this to what this would look like without multi-threading, it's still loading. That took 5 seconds. That is a 10 times difference. That's actually insane. Okay, so I got multi-threading working. However, somebody decided to ruin it. Somebody has single-handedly broken my program. Because they've done the notation in a way that the parser does not understand, meaning I'm probably now going to have to write my own extension to the parser just for this. Okay, time to show you how this works. So, first of all, we get the version data as fast as possible, and I'll explain this in a minute. All you need to know is that we create a channel and we pass the sender into the install package function, as well as the client and the version data. We pass the client in because this means that we can use connection pooling, which will make the connections a lot more efficient. First, we grab the package destination and the tarball URL from the version data. I'll explain these two functions in a minute, but we create a new Tokyo task, and inside this task, we asynchronously get the bytes for the package tarball file, which is just a compressed version of the package. The next task is to extract the bytes into the cache directory. What I previously did was extract the tarball inside the Tokyo task, but because this is a synchronous function, not asynchronous, synchronous, this means that it actually blocks the task from continuing, meaning that Tokyo is not able to optimize it properly. And I noticed when benchmarking that when I removed this line, it significantly improved the performance. So what I'm now doing is I'm sending the package destination and the bytes inside the channel, which is then received by this blocking thread. This creates a new native thread on this system rather than an asynchronous thread in the Tokyo thread pool. I could be wrong there, but I think that's how it works. But when we receive the package destination and the bytes from the sender, then we just extract it synchronously. Now this is where some recursion is required, is we get all the dependencies from the version data, and then for each dependency, we parse it and then get the version data for that dependency, and then recursively call the install package again. Notice how we're not using .await here or here, and that is because that would actually mean that the tasks run one by one, and we don't want that to happen. We want them to run together. Now we have a problem because all these tasks are running in parallel, but we have no way of actually knowing when we can finish the benchmark and continue on the main thread. Now, this is a little inefficient, but it's not the end of the world. It's not going to cause a big problem. But for every task and every thread we create, we increment a atomic use size. An atomic use size is something we can use across threads globally in the program. Now, for every new task, we increment this, and when a task is complete, including the Tokyo task and the spawn blocking, then we decrement this. And right after we call install package, we're basically blocking the main thread until the task count is 0. And then finally we can save how long that actually took. Now, massive credit to Avoidance, linked to his GitHub in the description. He explained to me how I could use channels to do this, and how we could actually keep track of the blocking thread. Let me quickly show you another optimization I did. So we're basically just checking if a package is already being downloaded in the clean install. So we have a hash map of all the dependencies and their versions, which is an arc mutex, meaning we can use it across threads. And then inside the already resolved function, we're checking if that's already installed and returning true if so. Otherwise, we return false and we add it to the hash map. And then this part of the loop will return if it returns true, so we make sure we don't install that dependency. Okay, so it's time for the moment of truth. Are we faster than Bun? Now, there's this really cool thing called hyperfine. It's quite difficult to benchmark HTTP because the speed can be quite unpredictable. And we also have this prepare command here, so it makes sure that it removes the Bun cache and it also removes the files from my cache. So, moment of truth, let's run it. Okay, so Bun is faster by 1.01 times. So we're basically as fast as Bun. Okay, so in this scenario, we are like 2 times slower than Bun, but we're going to do a few more benchmarks on different packages as well. Okay, so in this case, we are actually 1.3 times faster than Bun. So this just proves that it really does depend on the dependency. It's quite unpredictable. But besides that, even if we are a little bit slower than Bun, we've been able to pull this off on our own with the help of Avoidance, so I am really happy with that. Stay tuned in 2 weeks for part 2 where we add caching. Hope you've enjoyed and I hope you've learned something. I'll see you soon.